Welcome to the Cosmic Frontier, where today we unveil the secrets of the universe through the lens of the James Webb Space Telescope, JWST. In this episode, we're diving into a recent revelation that's stirring both awe and mystery within the scientific community. Prepare to embark on a journey to explore an image so profound, so unsettling that it was initially kept from the public eye. Strap in as we unravel the enigma of this terrifying new discovery and what it implies for our understanding of the cosmos. 3 decades following its conception, the James Webb Space Telescope was launched from French Guiana on Christmas Day. 2 years ago, specifically on December 28th, it journeyed past the moon. On January 24, it activated its engines for 5 minutes, propelling itself into its ultimate orbit, situated 1.5 million kilometers from Earth. After several months of meticulous preparation, it produced its inaugural image on July 12th of the previous year. This groundbreaking image unveiled distant galaxies as they were over 13 billion years ago, offering us an unprecedented glimpse into the cosmos. Since that landmark achievement, the Webb telescope has continued to expand on its remarkable legacy, marking a new chapter in astronomy and space exploration. Its latest images stand as a testament to humanity's relentless pursuit of knowledge and our inherent modesty in the vast expanse of the universe. Join us in examining the newest discoveries made by the James Webb Telescope, which are unveiling the mysteries of the cosmos. In reality, when telescopes capture light from faraway galaxies, they are not literally looking back in time. It's impossible to directly observe the past since it no longer exists. Instead, these telescopes allow us to study the light that has traveled across the universe to reach us, offering insights into the history and evolution of galaxies. We're examining the present configuration of a light beam that has traversed the vast emptiness of space, largely untouched, for millions of years. This journey through space's vacuum has preserved the beam's pattern unchanged from the moment it was emitted by a distant galaxy millions of years ago. By studying this light in its current form, we can deduce characteristics of that galaxy as it appeared long ago. This process is akin to viewing a photograph of your daughter as an infant, years after it was taken. When you look at this photo today, you're metaphorically traveling back in time to see her as she was then. However, this doesn't mean you're actually seeing into the past. Your daughter has grown since the photo was taken, and there's no version of her still existing as an infant. Instead, you're observing the current pattern of light reflected by the photo's ink, which remains arranged in a way that represents how your daughter looked a decade ago. This preserved pattern allows you to glimpse a moment from the past, much like how the light from distant galaxies offers us a view of the universe as it was millions of years ago. Consider the scenario where you have a photograph of your daughter as an infant, and the ink pattern has remained unchanged for a decade. Now, imagine if acid were to spill on the photograph, creating a large white spot above your daughter's head. If you were to take this altered image at face value, as if looking back in time, you might whimsically think she was once observed by a UFO or a ball of lightning. Of course, with a bit of critical thinking, you'd realize you're not actually glimpsing into the past, but are instead looking at a present-day light pattern that has been modified from its original state a decade ago. In a similar vein, when we observe light from distant galaxies at observatories, we are making inferences about the past based on the light that reaches us today. If this light remains unaltered through its journey across space, it offers a more accurate snapshot of the past. However, light can change as it travels, influenced by factors such as the universe's expansion, known as redshift. Redshift alters the light's properties as it crosses intergalactic distances, but because astronomers understand redshift well, they can reverse these changes to accurately interpret the light's original pattern. This process allows us to deduce information about the universe as it was billions of years ago, despite the light's long journey and the transformations it undergoes. To offer a precise depiction of the distant galaxy as it was when the light first left it, the James Webb Space Telescope, JWST has expanded our knowledge far beyond the few galaxies previously identified from that era. A recent study highlights that the JWST has uncovered hundreds of ancient galaxies, possibly some of the universe's earliest settlers, existing just 600 million years after the Big Bang. These nascent galaxies showcased complex structures and areas of active star formation. This groundbreaking research is the fruit of the JWST Advanced Deep Extragalactic Survey (JADSA) collaborative international effort that gathered data over a month from two relatively obscure patches of sky, one near the Fornax cluster and the other within the constellation of Ursa Minor. This exploration revealed over 700 newly identified young galaxies, offering a window into the universe's formative years. Kevin Hain, an assistant research professor at the Stewart Observatory in Arizona and a leading author of the study, likened the universe's entire history to a 2-hour film, suggesting that what the JWST has revealed is akin to the first 5 minutes of that movie. He emphasized the significance of these discoveries, stating, "These are the galaxies that are starting the process of building the elements and complexity we see in the cosmos today." The recent findings facilitated by the James Webb Space Telescope, JWST, have shed light on the origins of the early galaxies and stars, which are responsible for the variety of elements we observe in the universe today. Utilizing data from the JWST pane, and his team identified 717 young galaxies within what could be metaphorically described as the universe's first 5 minutes, suggesting these galaxies formed between 370 million to 650 million years after the Big Bang. Remarkably, these galaxies span thousands of light years, feature complex structures, and are sites of prolific star formation across numerous clusters. Previously, the most ancient galaxies observable to us appeared merely as vague blurs, each potentially encompassing millions or billions of stars from the cosmos's infancy. Now, with enhanced clarity, we find that some of these galaxies are not mere smudges, but extended entities with discernible structures. Major space observatories, including the Hubble Space Telescope, the Chandra X-ray Observatory, and the now decommissioned Spitzer Space Telescope, have conducted extensive research on the two sky regions examined in this study, collectively known as GOODS South. Impressively, 93% of the galaxies JWST uncovered during the JADES survey had not been detected in previous observations. Prior to this, only the brightest and most extraordinary early universe galaxies were visible to us. These advancements underscore the JWST's unparalleled ability to peer deeper into our cosmic past, revealing previously unseen facets of the early universe. As we delve into the early turbulent stages of the cosmos, our focus shifts towards more typical, everyday galaxies, moving beyond the exceptional and extraordinary. This transition prompts a closer examination of how the universe evolved from a chaotic, dust-filled expanse to the clear, observable space we recognize today. The ultraviolet light from these stars reionized the universe, a process that unfolded over the next billion years. However, some researchers argue that outflows from supermassive black holes, similar to the one at the center of our Milky Way, might have played a pivotal role in allowing ultraviolet radiation from galaxies to spread. This, in turn, could have had a more significant impact on the universe's development than previously thought. In support of exploring these early cosmic periods, a second team has been investigating galaxies that formed between 500 and 850 million years after the Big Bang. This research corresponds to observing the universe at about 5 to 8 minutes into a metaphorical 2-hour movie depicting its entire history. In the unfolding narrative of the universe, researchers believe they've found answers to long-standing questions about the early cosmos. As we peer deeper into the universe's history, we're beginning to witness the profound influence of galaxy formation on the cosmic landscape. Galaxies from these nascent stages were inherently more tumultuous, especially in their star formation processes. To shed light on how starlight ionized gas within these ancient galaxies, ESA's team delved into the signals indicative of star formation. These signals become detectable when ionized atoms, energized by starlight, cool down and combine with other molecules. The team found that 1 in 6 galaxies from that epoch exhibited intense emission lines within their spectra, a clear sign of vigorous star formation. This frenetic activity generated a flood of ultraviolet photons, making these early stars key agents in the universe's reionization process. SLI's research posits that such strong emission lines, signaling rapid star formation, were not outliers but rather common features in the early universe. These emission line signatures, indicative of intense recent star formation, were found in nearly every galaxy the team has discovered to date, highlighting their pivotal role in shaping the cosmos's early days. In their exploration of the early cosmos, ESA's team discovered that galaxies were adept at forming hot, massive stars. Through analysis of specific emission lines, they concluded that star formation in these early galaxies occurred in intense bursts, followed by periods of dormancy. The James Webb Space Telescope's first dispatch in July 2022, a detailed field image showcasing hundreds of galaxies, many as they existed in the universe's infancy, caught many observers off guard. Some galaxies appeared oddly distorted and twisted, reminiscent of Salvador Dali's surreal landscapes or melted candy, but this was merely an optical illusion created by the telescope. Another intriguing aspect of the Webb images was the appearance of galaxies seemingly duplicated within the same frame, as seen in the image of the massive galaxy cluster RxJ 20229. Again, this was an illusion. These galaxies do not actually have identical twins. The phenomenon responsible for both of these visual quirks is gravitational lensing, a concept first predicted by Albert Einstein over a century ago. This mechanism acts like a cosmic magnifying glass, bending and amplifying the light from distant objects. The images that appeared deformed or duplicated are examples of objects that have been gravitationally lensed, showcasing the profound effects of gravity on the fabric of spacetime and offering astronomers a powerful tool for studying the universe. Einstein's theory of general relativity, which posits that objects with mass can alter the fabric of space and time, collectively referred to as spacetime, explains the phenomenon of gravitational lensing. Picture a rubber sheet stretched out and sprinkled with balls of different sizes and densities. A ball with greater mass will warp the rubber sheet more significantly. Similarly, in the cosmos, the more massive an object is, the more it distorts spacetime, with galaxies and galaxy clusters serving as prime examples of such massive objects. When light from a distant star or galaxy passes near these massive objects, the path it takes becomes profoundly interesting. Although light typically travels in straight lines, it bends around massive objects due to the warping of space. As a result, the distant object seems to be located in a different part of the sky when its light finally reaches Earth. This bending effect is particularly pronounced when a massive object lies between Earth and the light source, causing light to take various curved paths, each distorted to a different extent. This warping affects not only the direction of the light's travel, but also the time it takes for the light to reach us and the path length it covers. Consequently, a single celestial object, when observed through the lens of gravitational warping, may appear to be in multiple places at once during a single observation. This intriguing aspect of gravitational lensing showcases the profound impact of mass on the structure of the universe, as predicted by Einstein's theory. Gravitational lensing can create captivating visual phenomena, such as crosses, or, in instances of perfect symmetry, a light ring referred to as an Einstein ring. These effects result from the repeated imaging of the same celestial body. However, as pointed out by the European Space Agency, galaxy clusters often serve as less than ideal lensing intermediaries due to their irregular shapes and the uneven distribution of their mass. This irregularity can cause the background object being lensed to appear as warped arcs around the galaxy cluster in observations like those seen in the Webb Deep Field View. Despite their peculiar appearances, these lensing artifacts offer more than just visual intrigue. Astronomers leverage gravitational lensing for its unique ability to distort and magnify the light from distant objects, such as early galaxies. This magnification is crucial for the Webb Telescope's study of the early universe, as it brings faint, far-off celestial objects into clearer view. Moreover, the specific patterns created by lensing objects can reveal detailed information about their mass distribution, both in individual galaxies and galaxy clusters. ENASA has highlighted that gravitational lensing can also uncover characteristics of celestial objects themselves. For instance, it has been used to detect water vapor in the atmosphere of the superhot gas giant exoplanet WASP-18b, which orbits its star in less than one Earth day. The James Webb Space Telescope identified WASP-18b as a gas giant with a mass approximately 10 times that of Jupiter, demonstrating the diverse applications of gravitational lensing in contemporary astronomical research. WASP-18b, an exoplanet significantly larger than Jupiter, the largest planet in our solar system, follows a remarkably close orbit of just 3.1 million kilometers around its sun. Like star, WASP-18, located approximately 400 light-years from Earth. For context, Mercury, the solar system's innermost planet, orbits the sun at a distance of 58 million kilometers, making WASP-18b's proximity to its star extraordinarily close. This close orbit subjects the planet's atmosphere to extreme temperatures, hot enough to break apart most water molecules. ENASA's analysis highlights the James Webb Space Telescope's Webb's exceptional observational capabilities, as it can detect residual water vapor signals in the exoplanet's atmosphere, despite surface temperatures soaring to about 5,000 degrees Fahrenheit. The atmospheric spectrum of WASP-18b reveals distinct, though subtle, water signatures, a remarkable finding given the extreme conditions that should theoretically destroy water molecules. This discovery underscores the Webb Telescope's unparalleled sensitivity. WASP-18b has been the subject of study by other telescopes, including the Hubble Space Telescope, NASA's Chandra X-ray Observatory, the Exoplanet Hunter TESS, and the now decommissioned Spitzer Space Telescope since its discovery in 2008. However, none of these observatories possessed the sensitivity to detect the detailed atmospheric features that Webb has, showcasing the advanced capabilities of this latest space telescope in contributing to our understanding of exoplanets and their atmospheres. The presence of water in the atmosphere of WASP-18b was elusive in previous studies, as the water signatures in its spectrum were too subtle for earlier telescopes to discern. However, the Webb Telescope's observations have enabled us to detect these water features for the first time, marking an exhilarating breakthrough in our study of the exoplanet. WASP-18b is not only exceptionally large, hot and close to its star, but is also tidally locked, meaning one side always faces its star, while the other remains in perpetual darkness. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blesovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.